Hello all and welcome to this hopefully short video where we look at the applications of circular functions. We're going to look at two examples. First example we'll do CAS free or tech free, and then the second example will be tech active, where I'll just more be pointing out some tips and tricks for you to use in doing the problem. So we'll roll through question one and example one. Half a question or example one has already been done, a bunch of the work, but we can still make some notes beside it and some key information or strategies that we used. So let's get going. So example one, the temperature T degrees during one April day is given by T equals 17 minus 4 sine pi on 12T, where T is the time in hours after midnight. In any applied problem, okay, this sort of information is key, okay, because this gives us a frame of reference. Because all the questions are going to ask, oh, what is the temperature at 2 p.m.? What's the temperature at 3 p.m.? When is the temperature 13 degrees? You need to recognize that our equation using T is based on some frame of reference or point of reference. In this case, when T equals 0, it follows on that it is midnight. Okay, so there's a point of reference that we can work from. And it asks, very first question, what is the temperature at midnight? Well, midnight is T equals 0. So we substitute that in. Okay, so all we've done is sub in T equals 0. So we got temperature is equal to 17 minus 4 sine 0. Sine of 0 is 0. So that turns into 17 minus 0. So we get 17 degrees. So pretty straightforward. What was the minimum temperature during the day, and at what time did it occur? Okay. Now, if we were doing this tech active, we'd be like, oh, minimum. I'll graph it. I'll look when the minimum is, bam, find it, or use function min whenever it occurs. Okay. But what if we're doing tech free? Well, are we, and especially we need to think logically, oh, this is given to me part B of a question. This will happen in exams, year 12 exams as well. It's given to me part B. I haven't had to sketch, it hasn't asked me the period, it hasn't asked me any of that. Is it likely that I'm going to need to do all of that to answer this question, especially this might only be a 1 or 2 mark, or probably in this case a 2 mark question? And the answer is no. Like, even my first instinct was like, okay, I've got the function 17 minus blah blah blah. I need to sketch the graph and have a look, and then then make an estimate and maybe know the period and find the quarter point of the period. That might be the first minimum, depending if it's inverted head. All of that sort of idea. But as the notes say, there is a much easier way to do this, and that's by looking at the question and interpreting in terms of identifying the key components. So we could rewrite this as T equals negative 4 sine pi on 12T plus 17. We could write it in that form. And from that, we can see that our amplitude is 4 and our B value, or our vertical translation, is 17. So we know really briefly that is at y equals 17, and we have some, and because it's a negative it goes down, we have some graph doing that. And we know the amplitude is 4, so if that's 17, my amplitude needs to go up 4, and importantly for this problem, because we're finding the local minimum, my amplitude also goes down minus 4. So my minimum point, the temperature at that point is 13. And we've done that just via inspection. We used the negative 4 and the 17 together. So my minimum temperature, what was the minimum temperature? Straight away we can go T is equal to 13. And at what time did it occur? Okay, so then we need to substitute in to give me t, fine, little t. So temperature is 13 is equal to 17 minus 4. We start to rearrange, so take 17. The in-between step is that it's -4 equals -4 sine blah 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 in there. Divide both sides by -4, we get 1 equals sine pi on 12t. Okay. Well, sine of what angle? This we could think of if we do it in long term. Sine of what angle gives me 1? Well, alpha is going to give me alpha needs to be pi on 2. Okay. So the other way we could write this is that we get inverse sine of 1 is equal to pi on 12t. So what angle gives me a vertical component of 1? Well, that angle needs to be pi on 12. So pi on 2 turns into pi on 2 equals pi on 12t. And it looks like maybe my PowerPoint's going to crash. Oh no, it's come back. Which is what this step here is showing. And then we solve and it gives us t equals 6. Okay. Now, it's asked what time does this occur? If you give me t equals 6, that's not telling me the answer. I could interpret the answer from there, but you want to be clear. What time does this occur? Well, using our point of reference, t is the time in hours after midnight. Okay. Min temp is at 6 a.m. using our frame of reference. Part C, continuing on with this question, over what interval did the temperature vary during the day? Okay, so again, we know briefly from the previous point, y equals 17. Y equals 17, and the graph is doing that, and we're down 4, and we're up 4 from our amplitude. Well, we know the minimum is at 13, and we know the maximum, 17 plus 4 is at 21. So, looking at the vertical translation and the amplitude, okay, the temperature will vary between 13 degrees and 21 degrees. Now, another word for vary that you might see is oscillate, okay, or move between. There are other words that might be used in a similar sense. So I might say, what two positions did something vary or oscillate between? Well, that means what did it go between its min and maxes? State the period and sketch the graph of the temperature for t is the element of 0 through 24. Well, using our period that we know is 2 pi on n, and in our case the equation n was pi on 12, n equals pi on 12. 2 divided by pi on 12 equals 24. That's nice and handy. So our period actually matches our graph. So we don't have 24 blocks, but we probably will fit 12 in. So we could make each block equal 12. So 1, 2, 3, 5, 6. So we'll make that 12. So that'll be 6. 1, 2, 4. That'll be 24. Make that 18 hours. And because we're not dealing with any horizontal translations, let's maybe say that there is 17. We'll go up here. We'll say that's 21. And say that's 13. Is that a workable scale? 3 blocks to 13. Yeah, not really. Probably a more accurate vertical scale would be to say that's 21. And that's 13. somewhere around there. But again, we don't need to be perfectly exact, but we need to at least have some form of consistency. So we have that. Now it is a negative. Okay. That means it's been reflected. So instead of sine, the normal sign goes up first, but since it's reflected, it goes down. And we know the period is 24. Half the period will be back at its starting point. That'll be halfway at 12. And then we can split that into what effectively we know the quarter point and the 3/4 point. We can graph. Let me go to a different color. Like that. Okay, and then we just have to label the key information. So that is 7, not 17. That is 0, 17. Our quarter point is at 6, 13, which we also knew from part B back here. Minus 6, we got a minimum of 13. We can label this point, it's easy enough too. It's 6, 17, half of our period. We're back. Equivalents are 3/4 point. We are at 18, 21, and our last point is 24, 17. That's that graph. And then find the time or times when the temperature is 15 degrees. Before I go on with that, I want to point out, what would it, say if the question asks, at what time was the temperature 21 degrees? Well, we can look right here. So if we're asking, what time was it when temperature, capital T, was equal to 21 degrees? Well, we can see this was, I should have labeled my axes, capital T, small t, and that's in hours, and this is in degrees Celsius. Okay, if you went and told me that t is equal to 18, well, yeah, reading off the graph it is, but what is the time when that occurred? Well, midnight plus 18 hours, time is 6 p.m. So you've got to be able to interpret from that frame of reference. Right, find the times when the temperature or temperatures is 15 degrees. So we're going to let capital T, our temperature, equal 15 degrees, sub, and solve. And so we substitute in 15 equals 17 minus blah 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 blah. So let's start solving this. We are going to get negative 2 equals negative 4 sine pi on 12t. So divide by negative 4, we get half equals 9 pi on 12t. Okay. Now you could do the full substitution, as in let pi on 12 t equal to alpha. Okay. But we could also write and keep going with that method. That's completely fine, but the quicker method is to go, well, inverse sine of half is equal to pi on 12t. Now, inverse sine of half, what is that asking? What is this asking? Okay, that says what angle is a sine value vertical of half? Well, if you use your, if you remember the exact values, or you can use the hand trick, half sine, that's 1 up, that would be pi on 6 equals pi on 6. Okay. But, okay, during this event, we get one full cycle. Okay, so that means we know there's always two solutions within a unit circle. We also get a vertical component of half at 5 pi on 6, which, just to be clear, comes from pi minus pi on 6. We've got that's pi equals half. We have one solution there, and then we have another solution there, which is actually all the way around and then back, which is that pi minus pi on 6. Rid of all of that. Rightio, pi, so we have pi on 6 comma 5 pi on 6 equals pi on 12 t. So we're going to get pi on 6 divided by pi on 12, 5 pi on 6 divided by pi on 12 equal to t. So that's going to be 12 on 6, that's going to turn into 2. And that's going to turn into 5, 12, 6. So 5 times 2, that's going to be 10. Okay. Now, using our frame of reference, knowing t equals 0 at midnight, that's going to be 2 a.m. and 10 a.m. If we go back to our graph, we could put that in. We know 15 is about there. Okay. So it will be 1 time then and 1 time then, which, yeah, that looks about right. That was the 2, and that's 10. So our graph even had a relative accuracy with the scale. And that's all done. So this is where having a graph and recognizing you could have drawn this, that would have been another strategy. I left it till the end to show you, but you could go back. It's like, okay, I need to find when it's 15. I go back and look, drawing 15. Okay, it's roughly going to be here. Oh, there's going to be a second solution, or it could be if this graph kept going on and on and on, we would have third and fourth solution. So looking at it and drawing in rough sketches on a graph will help with you identifying how many solutions you need. Okie dokie. So that's it for the tech free. A couple things to note there: your point of reference and how you can do the question efficiently, and that a lot of the time relies on looking at how long the period is. If we're dealing with, in this case, it was time. Any problems to deal with time, you want to be thinking in terms of your period. That can give you a shortcut. Or since we're thinking vertical, which is a temperature in our case, then you need to think in terms of the center point and then your amplitude. So your center point is given by your vertical translation, and your amplitude is your amplitude. That can get you 95% of the way there without having to do any complex algebra. Okay. Example 2, CAS active. So what I'd suggest right here is actually pause the video and take 15 minutes. Give yourself 15 minutes to have a crack at this. How would you go about it? Okay. Have a go, pause, see how you go, and then you can come back and I'm going to give some hints in a second on how I do each of these, or some important things. Right, so let's be honest, I'd hope all of you would have paused and had a go for 15 minutes, but I know some of you won't, so let's keep going. During a particular day in the Mediterranean city, the temperature inside an office building between 10 a.m. and 7:30 p.m. fluctuates. So T hours after 10 a.m., the temperature 2 degrees Celsius is given by this equation. Okay, so this is our frame of reference. T hours after 10 a.m. So if T equals 0, it's 10 a.m. Okay, so we're not starting at midnight anymore, we're starting at 10 a.m. Okay, state the maximum temperature and the time it occurs. Okay, how could you do it on CAS? Well, you could graph it. State the minimum temperature at the time it occurs. graph it. Okay, stating the maximum and the minimum, we can do exactly the same as the last problem without even having to touch our CAS and do it really quick. Well, the maximum is going to be 19 plus 6. It's going to be 25 degrees. And the minimum is going to be 19 minus 6. Looking at that, equals 13 degrees. Okay. The time it occurs, use your graph. Use your graph using trace or min and max functions. Or you can use fmax and fmin. Before we go any further, if you're graphing this, and I'm not going to give you the actual solutions because you can just read them off your CAS, is I would have defined, okay, so on my CAS, the first thing I would have put in is, if I can spell, define f of x in this case is equal to 19 plus 6 sine pi x on 6. Okay, because to graph we need to change the variable to x, and then I would have put given, okay, and we're actually given a domain right there between 10 a.m. and 7:30 p.m. So we know our time, okay, t is between 0 and, to go to 7:30, that would be 9.5 hours later after 10 a.m. So I would put this given symbol in, and I'm just going to have to write on the next line and write exactly that. 0x 9.5. Why would I do that? Well, that reduces the amount of graphing the CAS has to do, and then if I do an auto window zoom, then it's not going to try and fit on and on, because as we know, sine goes on and on and on and on unless we specify a domain. This instantly allows us to solve graph a lot better with the actual given domain. And I can look at and then find, am I getting a full cycle in? Is there less than a full cycle? Because if there's less than a full cycle or more than a full cycle, then that creates issues for our min and max problem. We can't just assume straight off the 19 plus 6 or the 19 minus 6. What is the temperature at the building at 11:30 a.m.? Well, that's just f of 1.5. Whatever that gives, answer to one decimal place. Done. Because 11:30 a.m. is 1.5 hours after 10 a.m. What is the temperature at the building at 7:30 p.m.? Answer to one decimal place. Well, that is just f of 9.5. Same thing, it's 9.5 hours after 10 a.m. Sketch the graph of the temperature against the time from 10 a.m. to 7:30 p.m. Okay, well, you've found the max and the min, so you can put that on your graph. You've got another point of reference at 11:30. You've got your 7:30 p.m., which is your end point, so you have that fine. The only thing you need to find is find the temperature at 10 a.m. For your starting point. All the rest of it, and you can get that pretty quickly from your CAS. When the temperature reaches 24 degrees, an air conditioner in the boardroom is switched on, and it is switched off when the temperature of the rest of the building falls below 24 degrees. How long is the air conditioner on? Okay, so we need to solve for when f of x is equal to 24. Okay, and we'll get multiple solutions, and again, that's good that we've got a defined domain. Okay, and then we can read those values as the start and end time. We'll get a start and an end time for when it's above and below 24. And you can also look on your graph, and then for how long, it asks how long. So we need to find the difference between our start and end. And we need the difference between these in amount of hours. The office workers who work the shift between 11:30 a.m. and 7:30 p.m. complain that the temperature comes too cool towards the end of their shift. The management agrees that heating can be used for the coldest 2-hour period of their shift. At what time and at what temperature would the heating be switched on? Express the temperature in both exact form and one decimal place. Okay, now this again depends if a full cycle's fitting in. If a full cycle's fitting in, okay, if we can fit in a full sine graph, the coldest 2-hour period will, let me draw this a bit bigger, the coldest 2-hour period will be 1 hour either side of the minimum. Okay? And you found the minimum temperature and when the time occurs. So you could use that straight away. 1 hour minus that, 1 hour plus that. And that's when it would be the coldest 2 hour block. You just need to find what time that occurs, okay? Which would just be this answer here, -1 and also +1 for the time. And yeah, that would be it. The only thing we're relying on here is that the coldest 2 hour block, we aren't cut off at some stage. Like it might be, I haven't graphed this problem in a while, but it could be that 7:30 p.m. is right there. That means we need to work backwards 2 hours. So again, looking at your graph and having the defined domain, everything relies on this, how we approach the problem. So I would always sketch it with that domain. That's about it, about how you'd go about it. To get the exact values, you would do that. You wouldn't try and read values off the graph. You would have to use f of whatever your time is, and then or the temperature that you're solving for, and do that in the algebraic component of the CAS rather than reading off the graph. Because you just try and read off the graph using your trace function or whatever, it's always going to give you it in decimal places. It won't give it to you in exact values. So that one you'll have to do it algebraically on the CAS. That's it from me. If you have any questions, ask as always in class or shoot me an email. Thanks and bye.